Hi, my name is Meena Kaur, and I am majoring in electrical engineering. I will be speaking today on the subject of DC motor control. DC motors have several different designs, but the simplest use a stationary magnet and a rotating armature. The armature receives its power from a pair of carbon brushes resting on sets of commutators. DC motors have the benefit of accurate speed control, quick starts and stops, and relatively high starting torque. Common uses for DC motors is in portable robotics, moving toys for children and adults, cell phones, elevators, printers, and many digital systems. The system overview will include the design specifications, a system model, open and closed loop responses, and basic transfer function overview. In this project, we are modeling the armature-controlled DC motor. The rotor and shaft are assumed to be rigid, as directed. We assume a viscous friction model, with a friction torque proportional to the shaft angular velocity. This motor is modeled with a single voltage source input, with angular velocity being the single output. All motor specifications were obtained from Elwood Motors specification sheets for the M111 4 inches diameter DC motor. With a rotor inertia, J, of 0.01 pounds-inches seconds squared. A viscous damping coefficient, B, of 0.715 pounds-inches seconds per radian. A back EMF constant, K, of 0.0341 rotations per minute per volt. Armature resistance, R, of 1.045 ohms. And an armature inductance, L, of 0.0035 henries. The block diagram simplifies to omega over V, equals K over the quantity of R plus Ls, times the quantity of Gs plus B, plus K squared. Using the inputs specified, the final value, which is 0.0456, should be 1. The current rise time is 0.0322 seconds. The desired settling time is to be under 0.4 of a second, with less than 5% overshoot, and a steady state error of 0%. Using this ISO tool, a root locus was found that achieved the settling time and percent overshoot goals. The values at this point are 0.0229 seconds and 4.06%. After finding the first real zero, a PD controller can be implemented. This achieves a settling time of 0.0186 seconds, and a percent overshoot of 0.771%, but the peak amplitude, at 0.564, is not near the unity value that is desired. Implementing the integrator and a second real zero, helps bring us to our goal. This achieves the peak amplitude goals. In order to improve the time response of the system, the compensator gain is increased. With the gain all sorted out, the final values are percent overshoot of 0%, a settling time of 0.346 seconds, and a steady state error of 0.002%. Here we have the basic PID controller system model. With a relatively efficient motor, an efficient PID controller can be developed. This is necessary for rapid designing and prototyping without extensive trial and error. All of the trial and error can occur during the modeling phase. Thank you for your attention today. Please thank Daisy from www.fromtexttospeech.com for her service for the voice in this presentation. There are many voices and languages available for all text-to-speech needs.